the square of the voltage. So unless you just magically happen to be using exactly the same voltage that the manufacturer tested it on, we've got a problem. We don't know what this value is, and it changes with the voltage. A better way of doing it is to measure the leakage of the inductance, the leakage inductance of the transformer, which we've already done in a previous video. We can do that with a Bode 100. And then measure the ringing frequency. We can very easily measure this ringing frequency here, and that gives us FR. Once we have then we have FR,
we can make
L,
leakage
calculate C, which is the parasitic C here.
So
then we can
this is basically, we don't know which value, because it is not real capacitor. It is basically.
On the green trace here is really very, very little damping. This is a simulation. If I assume that Q is equal to 1, then I can simplify all the equations that I gave you into this. Right? Again, please don't worry, we've got a spreadsheet that you can download that this will design everything for you. But for a Q of 1, R has to be equal to 2 pi resonant frequency times the leakage inductance. This one we know because we measured with our Bode 100 in an earlier video. This one we can easily measure using an oscilloscope from there to there. 2 pi we know, and therefore we can calculate R.
So we can calculate that
value of the capacitance
is mesh.
Now, this is only an approximation. And what you see here, the green trace, the blue trace, and the red trace is different values
if you
of the
put any number in its
the larger
libraries,
the value of the
after you put a number
the
in its
better the
libraries,
damping and the
so
more
it can reduce the reading and also spike.
Unfortunately, the power loss is actually the snubbing capacitance times the square of the voltage that is across the
loss
times the switching frequency. And as you can see, if you use a too big a capacitor in order to get a very nicely snubbed voltage without any ringing, your power loss might be quite high.
If
so
you put
what
more
I tend to do is I tend to look at this part first and turn around and say, okay, you know what? For let's say a 1210 package, I try to limit the amount of power loss to between 50 to 100 milliwatts, even though you can buy a 1 watts package. The problem is that if you dissipate that sort of power, what will happen is you get a hotspot on your PCB and it's not getting leaking after a while. So to be really conservative, let's say 50 to 100 watts, that's milliwatts, and therefore, you know the switching frequency, you know the voltage across the snubber, that is the voltage referred. We talk about that. You can measure it, and then you say, I'm going to allow, I don't know, 50 milliwatts, and therefore you can calculate the snubbing capacitor. So then you end up with your switch, your capacitor, your resistor,
resistance. So this is this number.
And you can see that we have calculated R, we have calculated C, we know that the power loss is reasonable. So if you look at the green trace, that is a real measurement.
This is a measurement.
Flyback
without
power supply,
it is
and
like
I have measured the
so this is not good because it could damage your switch. If this is 100, this could be 300.
25 megahertz.
Immediately damage
so
your
to calculate my R, I have to do 2 pi times 25 megahertz. In one of the earlier videos, if I remember correctly, our total leakage as seen on the primary was around 200 nanohenries, and therefore you have calculated your R. Finally, you look at the voltage across the switch, or you can calculate it by referring the secondary voltage to the primary side, and you know the switching frequency, you know the snubbing, you know the power loss that you want, around 50 milliwatts, you know the voltage, and you can calculate the snubbing capacitor size without dissipating too much heat. Okay, so I have done that. We do this in a workshop, and then you, for the jumper, you can add in what you have for the snubber. So this is without any snubber. And this is
so this is better.
So please compare
Without snapper.
The green trace, whereby there is very little snobbing,
This
it's
is
just
without snapper.
dissipating naturally with the parasitic resistances on the circuit to this. I have measured the ringing
So
frequency.
maybe
I've calculated
3
everything.
times of the
And
voltage.
this is the one.
And then after the snapper. It's
If you're
better.
going to do a snubber for the secondary side, i.e. the diode on the secondary side of the transformer, the equations actually stay exactly the same. The only thing is that you have to work out the voltage across the diode. Apart from that, everything else will stay the same. Now, provided that you can make this capacitor big enough, this will be beautifully damped. But as you can see, this is actually quite high now, and then comes a point where the
reduce the
ringing
peak phase.
spike is so high that a very large value of
So we
capacity
can
will be
change
required, and at that
the
point,
resistance
we will power
capacitor
high.
to change the waveform.
At that point, we use what we call an RCD clamp.
So
And
this
we're going
is
to talk about that
RCD
in a different
snapper.
So, hope you enjoyed the video. There will be a spreadsheet that you can use in order to do all these calculations. All you need to do is make your measurements and type them in. Hope you enjoyed it. Thank you very much.
Okay, then we can watch next one. So the first one is
Hi, my name is
snapper. Snapper circuit. And the second one is voltage important and the current important.
Why, hello. In this video, we're talking about inverters. And there are two main types of inverters.
So
One
two
is
main
called
inverters.
voltage source inverter,
Voltage
as
source
I for
inverter
short, and one
and
is
the
a
current source
inverter.
inverter.
The basic concept is that the source fundamentally
If the source
acts
is
like
DC voltage, we call voltage source important.
capacitor
Input is
or
DC voltage.
some
So we only discuss
that
voltage source important.
Then we would model our source as a voltage source. And then our inverter would be a lot of different switches, and they would transform the voltage into
So transform the voltage into current.
negative.
So we say
sometimes
this
zero,
is
depending on
voltage source important because this is voltage.
over the load. And the load is going to be AC, so it's going from DC to AC. And then the current in
DC
from the
to AC.
actual impedance
DC voltage to AC current.
That's the
So
basic
voltage
idea.
source
Within
important.
the inverter, there's a bunch of different topologies that you can use, but we're just saying when the source is a voltage source, then we can use a voltage source inverter to transform the DC to AC.
DC to AC.
The
DC
other
voltage
side
to AC current.
current source
So
inverter.
now we discuss a
And
new
this is where the
current source important. You need a
source probably has some sort of inductive.
current source. So this is voltage source. This is current source. So we need a current source to convert to AC
Apologies.
current output.
The idea is that if you take that source and put it
So
in
we
the
call
in a
current source important.
or the negative direction, or sometimes zero if the current is
So two
circulating
times.
through the
Voltage
inverter.
source important.
Here's one of the
Current source
then you can
important.
see the current on the output. So the current source inverter kind of chops up the source into different positive, negative modes at the load. And then the voltage characteristics of the load are determined by the impedance. Here we're just using the Z.
So this is the
Both of these
impedance.
types of inverters are commonly used. Voltage source inverters.
So in general, we use voltage source. In special case, we use current source.
Like that, but the current source inverter is also used in various applications, especially larger grid connected systems.
This is a high power in general.
Generally,
high power.
inverters, or when someone has said inverter, they usually mean a voltage source inverter, and we tend to
So in
study
general,
that more
we
in
discuss
software,
this, but for
solely because
very high power,
they're just a
we
little bit
use this
easier for
current
most
source
people to
inverter.
understand. The voltage source inverter is usually what we will focus on. So, quick summary, voltage source inverter.
voltage source
Source
inverter.
is going to be more like a voltage source. So we use that. The inverter then puts positive and negative voltages over the load, and the current is determined by the characteristics of the load. The current source inverter
This is
assumes that
current
your
source
source
inverter.
is more like a current source. And so the current source inverter is a series of switches that will then take that current and transform it over positive and negative directions to the load, and then the voltage is determined by the impedance of the load itself. So these are the two types of inverters, and there's lots of different topologies, which we'll start to get into just a few of those in future videos.
Okay, and we'll watch the third video about current source inverter. What is current source inverter? So current source inverter.
Smart learning. In this session, we are going to discuss
Current source inverter. So what is current source inverter?
current source
The
inverter.
current source inverter convert input current into
In current source
AC
inverter,
current.
input current remain constant, but this input current is adjustable. The current source inverter is also called as current feed.
Current feed
The
inverter.
output voltage of inverter is independent of the load. The magnitude and nature of the load current depend on the nature of load impedance.
Okay, this is current source.
In figure, you can see this current source inverter fades index of modern time.
Different is before we use huge capacitor, but now we use huge inductance. So this is the difference.
Diode.
We try to create input current source, not input voltage source because of the inductance.
Convert it like this. From this.
So this the current is like this.
The diode given to D6 in capacitor C1 to C6 provide combination of thyristor A.
So we use thyristor,
Fired where
not IGBT, thyristor.
in the sequence of their number. It also shows the nature of the output current waveform. The inverter acts as
So
the
the
current source.
inverter current source
Large inductor.
due to the large inductance.
The fundamental
So not the voltage source,
motor
current source.
phase current is shown in the figure. The torque is controlled by varying DC-link current IT by changing the value of VD. When the supply is AC, control rectifier is connected with the supply inverter. When the supply is DC, chopper is interposed between the supply and inverter. The figure,
So this is the current
you can
source.
see the current source inverter.
We need a huge inductor, then we convert
The
into
major
current source.
inverter is its reliability.
So this is the
Case
advantage.
of current source inverter
Reliability
failure
is good.
the same like does
So
not
although you short circuit,
large inductor.
it is no problem. Although inverter short circuit,
Index
no
of
problem.
rise and fall of current
Because inductance limits the current.
current provide large motor spikes. Therefore, a motor of low leakage inductance is used. The conversion capacitance C1 to C6 reduce the voltage spike by reducing the rate of rising and fall of the current. A large value of capacitance is required to sufficiently reduce the voltage spikes. Now, the regenerative braking and multi-quadrant operation of CSI. When the motor speed is less than the synchronous speed, machine works as generator. The power flows from machine to DC link and DC link to and DC link voltage will be reverse. If a fully controlled converter is made to work as an inverter, then the power supply to DC link will be transferred to AC supply and regenerative braking will take place. Hence, no additional equipment is required for regenerative braking of DC motor drive. The drive can have regenerative braking capability and 4-quadrant operation if a 2-quadrant chopper provides current in one direction but voltage in another direction is used. The closed loop speed control
Closed loop
CSI
control of current source inverter.
drive of CSI drive is shown in the next slide. The actual speed of omega m is compared with the reference speed omega m star m. The speed error is controlled through PI controller and sleep regulator. The sleep regulator sets a sleep speed command W omega star SL. The
So
synchronous
this
speed
is
obtained by
induction motor control by using current source
omega star
inverter.
SL determines the inverter frequency. Constant flux is obtained when the sleep speed omega SL and LS have the relationship. Since IT is proportional to IS according to the equation shown below. A similar relation exists between omega SL and IT for constant flux operation.
So this is a graph
The
diagram.
diagram you can see the
So you can see we use a huge inductance, not a huge
You can see
capacitor
the
before the inverter.
component.
Then we can convert
This is
the
a fully controlled
input become constant current.
to the inverter.
So we call it is current source inverter.
This is the speed sensor.
So this is speed control.
Sleep regulator, flux controller, current controller, firing circuit, etc. Based on the value of omega star SL, the flux control flux produces a common reference current I star D, which through a closed loop current control adjusts the DC link current ID to maintain a constant flux. The limit imposed on the output of sleep regulator limits ID at inverter rating flux. Therefore, any correction in speed error is carried out at the maximum permissible inverter current and maximum available torque, giving a fast transient response in current protection. Thank you for watching this video.
Okay, so we finish.
Good friends, myself Vipul Patel.
So paper. So we watch 3 videos. So the 3 videos include 2 parts. The first part is snapper synchrony. The second part is current source inverter. So we will discuss in details. So first is snapper. Snapper synchrony. So if we have inverter or we have a switch, then we have a very simple control switch, this one. And we have input. So then if Q on, then we have constant current here. But if we have Q off, then what happens? Then we have current here. But then we have LDIPT. So the current original 10 ampere, but now reduced to 0 ampere in 1 microsecond. So if L is 1 millihenry, so what is the voltage? 10 kilovolt. So we have 10 kilovolt here. Then what about the switch damage? Because your current has no path to flow. The only way is change from 10 ampere to 0 ampere. But you have inductance, then the inductance create high voltage, 10 kilovolt. Then the 10 kilovolt damage the switch. So if you have no experience about snapper, then you damage your device every day because it is dangerous. We have a fundamental rule. If you have a current flow into the inductance, then you have to provide a path when you turn off the switch. So if you have a river just go this way. But suddenly you plant the river, then what happens? The water will flow to the whole city. Then we call it is flooding, right? So if during typhoon period, then the water is too much. Then they cannot go this way, then they just go outside. So if you turn on a switch for inductor, then you can get 10 ampere. But when you turn off, you have no case. If you have no case, then slow, you create spike. Then you damage your device immediately. And the next time you try again, you damage again. So there is no way to solve this problem. So now we want to discuss the details. So if you design a circuit like this, then in general, you could provide maybe diode here. So we have inductor here, we have inductor here, we have inductor here, we have current here, but sometimes we provide free-wheeling diode, maybe free-wheeling diode, something like this for this one. So we can draw the circuit again. If you have a real circuit, then you have switch here. So this is switch. And then you have a line. This is a line. This line from here to here. But if your operating frequency is so high, then you have a line. Then the line becomes what? Inductance, like straight inductance. So you create straight inductance or leakage inductance. So you have straight inductance. It is quite small, but you have inductance here. And then you have a huge inductor here. This inductor creates constant current. So you have constant current here. So you have a constant current due to the huge inductance. So you have constant current. And then you have diode. So you have diode. Diode here. But the diode you use a line, here a line, to connect. So this line is like this. And then the line creates a small inductor. And then you go here. And from here, you have voltage here, voltage here. But here, you use some line to have a capacitor and then have a voltage. But from here to here, you have a line. This line creates small inductor. Another small inductor, the one. And then this line you have another line. So you have small inductor here. And then you have capacitor. And then you have a line to source here. A line to source. A line to source. So you create a small inductor here. So the circuit becomes very complicated, like this. So you have straight inductance. It is small. It is only a line. But in a high frequency, the line becomes small inductor. Okay, so your circuit becomes this way. Then what happens? Every time you turn off, then you create LDIDT. Then you create a spike. Then the spike damage your device again and again. So we have to analyze this situation, and we have to find some way to solve this problem. So now we try to understand what is the reason and how can we solve the problem. So what is the problem? The problem is very simple. You have Q, so you turn on Q. So you have Q, you turn on Q. Then you turn off Q here. If you turn off Q, then the D on. D on. And the next time you turn on Q, then D off. So we have a current here. So we can either go this way or go this way. So we have two switch. So Q and D. When Q turn on, D should off. When D turn on, Q should off. If you over there, then what happen? Then short circuit, right? The voltage source short circuit, then you damage your transistor. So we understand that after Q turn on, after Q turn off, the D couldn't turn on before Q. If D turn on here, then what happen? Short circuit, right? So the D should be after Q. So we have to delay a few, maybe microsecond, then the D turn on here. We delay 1 microsecond. But the time is here. From here, Q already turned off, but D not turned on yet. So Q off, D off, right? Q off, D off. If Q off, D off, this off, this off. But you have current here. Then you have L3 dI/dt. So although this is only 1 microhenry, but you have 10 ampere go to 0 ampere in 1 microsecond, maybe 0.5 microsecond, then you can get 20 volt. So spike 20 volt. Then could damage your device. So the reason is you still have dead load. It is impossible to connect this perfectly. Q turn off, D immediately turn on. Impossible. Because diode has rise time, right? Every device has rise time. The rise time only 1 microsecond. This is called rise time. So although diode try to trigger, try to turn on, but after 1 microsecond, it becomes fully turned on. But before it turn on, Q already turned off. Then you have M here. And the Q turn off, D turn off, then spike. So there is no method can solve this circuit. So now we want to discuss the problem and propose some useful method. So now we want to discuss the turn off. So Q turn off. So we try to discuss the turn off transition. So now Q turn off here, turn off transition. So at T0, the transistor is on. It's conduct. So here, transistor is conduct. So here we have T0. Before T0, transistor is conduct. Then we have current go to the transistor. So we can say IC is equal to I0. So this is I0. So we go this way. So transistor current is equal to output current. It could be 10 ampere. Now we try to turn off the transistor. So at that point, at this moment, transistor turn off. So at that moment, transistor turn off at T equal to T0. Then what happened? Transistor turn off. So transistor turn off. Then we have a voltage. So across the transistor, because transistor turn off, if transistor turn off, then the voltage across the transistor increase, right? If transistor turn on, what is the voltage? Near zero. If transistor turn off, then the voltage across the transistor increase. So we have VCE. It is equal to VD minus the inductance voltage drop. Okay, so voltage increase. And what is the current? Because transistor turn off, so the current flow into the transistor is decreased. So the DIC dt is negative. It's negative. If this is negative, this is positive, this is negative. Negative minus negative become positive. So which means the value become large than VD. So after you turn off, the voltage across the transistor increase more than VD. So now we try to get this situation. So what is the waveform? So we try to draw the waveform of the circuit. So what is the turn off before we are turned on? So the transistor has IC. The voltage is zero, near zero. Okay, now the transistor turn off. So now turn off. Turn off. Q. Turn off the device Q. If we turn off the device Q, then the device current decrease. So it is decrease. Takes some time. And if the current decrease, the Q will become turn off, gradually turn off, right? If the Q gradually turn off, then the voltage increase. So Q turn off, then the voltage increase. And this is VCE. You want to reach VCE. However, due to this is negative, this is negative, this is positive. So the VCE larger than VD. So the VCE, this is VD. It is over VD, over VD. So you can see the transistor voltage induce a high voltage. So it could be 1 time, 2 times. So it creates a huge spike. So we call this is T1. This is T1. This is T0. This is before. This is Q turn on. So this is before T0. At T0. After T0. So now we go to T1. So then the voltage is larger than VD. Then what? So the voltage is very large, larger than VD. And then you have a small capacitor here. We call this is straight capacitor. This is straight capacitors. Because you have correct, you have emitter. This is correct, this emitter. You have 2 K, and then we have a small capacitor here. Because 2 lines, right? If you have 2 lines parallel, then what happens? Capacitor. If you have 1 line, then what happens? Straight inductance. If you have 2 lines, then capacitance. So you have a straight capacitor, then what? Oscillation. So this one start oscillation. Okay. So if you design a snubber, then it is good. Then it will start here. Okay. So we start here. So now the Q turn off. If Q turn off, current becomes 0. voltage become VDC in steady state, right? Okay. So this is turn off time. How about turn on? If you turn on here, turn on here. If you turn on the device Q, then what happens? Then the voltage will decrease. So you have a current here. So now you turn on. You turn on the device. If you turn on the device, you have a gate signal turn on. Then the current increase, right? Because you have LDI/dt. It is equal to VDC. So dI/dt is VDC divided by L. So it is positive. Then the I is from 0 and then increase with time. So the I just increase. So we can see now we turn on. Then what happened? The current increase. And it is larger than IC. So this is IC. But it is larger than IC. Then it return to IC. So now we turn on and the current increase. If the current increase, then what happened? The voltage decrease. So the voltage decrease and reach to 0. So we have turn on and turn off. Then what is the behavior? So for your device, you have turn on and turn off. Now we want to create the curve. So we have a switch. We have T0. T0. What is T0? T0 is here. So at T0, what is VCE? VCE is 0. So VCE is, this is VCE. VCE is 0. This is VCE, right? And how about current? Current is IC. So we have a current. The current is IC. This is IC. So we have IC. So at this point, voltage is 0. Current is IC. Now, what happened? You try to turn off. If you turn off, what is the current? Current decrease. So current decrease. And how about voltage? Voltage increase. So we can see voltage increase and the current decrease. So how can we describe the behavior? Voltage increase. So we can see this one. Then voltage increase here is larger. Then we have a voltage increase here. So voltage increase. And the desire is here. But now we real curve is here. So voltage increase and it become larger than VCE. So this is VCE. Then the voltage is larger than VCE here. After that, so larger than VCE. And then it go back to DC voltage. So it go back to DC voltage. So it is like this. So now you turn off the device. If you turn off the device, how about the voltage? Voltage increase and larger than VCE and then equal to VDC. So the voltage increase larger than VCE and go back to VCE. So we call this is trajectory. So this point is T1. So this is voltage curve. So we can draw the voltage curve. So and then it reach steady state. So we have this point, we call this is T3. T3. So this is T3. And T3 it reach to steady state. So we have this curve. And then next time you turn on again. If you turn on again, then what happens? This is T4. And this is T5. And this is T6. So you turn on again. So at T4, T3, you turn on again. If you turn on again, then how about your current increase? So this is current is 0. Now your current is increase. So we can see this is increase and reach to T5. So T5, your current increase reach to T5, reach maximum current. So maximum current. And then what happened? Your current decrease to steady state. Then your current decrease to steady state. So decrease to steady state. So go to the steady state, go to IC. So this is T6. This is T5. So we have a trajectory. The curve go this way, go this way, go this way, go this way. So we can see this is the trajectory of turn on and turn off. So we can understand we have this trajectory. So the voltage is not only reach VDC, VCE, it is more than VCE. So if you select the voltage stress, if this is 200 volt, then you cannot choose this voltage stress is 200 volt. You should choose it could be 300 volt because it is large than VCE. So you can see here. So we have this kind of trajectory. So then we have to consider this situation. So if you have an inverter, inverter is like this. It is like this. So this is inverter. And we have motor. Here we have a motor. So we have a current signal here. So this is T1. This is T1 plus. Then we have to design some circuit. This is Q1. This is Q2. So you have trigger T1. So T1 is turned on here. And then if T1 turn off, you have to turn on T1 plus. If you turn on T1 and T1 plus, then what happens? Short circuit. So we have 200 volt short circuit. So you have to make sure after T1 turn off, you can turn on T1 plus. So you have to keep this way. So you have daytime here. But during the daytime, T1 turn off, is turn off. T1 plus not turn on yet. Then what happens? You have 100 ampere here. You have huge inductor here. Then this is current. But the current has no base, right? Then what happens? So this is huge current. And your motor, 100 ampere, go to 0 ampere in 1 microsecond. Then you can calculate So this is voltage. Then what happened? Damage everything, right? So you can see I cannot turn on Q1, I cannot turn on Q1 and Q2 together. So after Q1 turn off, if I want to turn off Q1, I just turn off Q1. But I have to wait during my waiting time. Then this turn off, this not turn on yet. Then no test. But I keep 100 ampere here, right? I have huge inductor. Then a huge spike here. Then what happened? This one and this one, both of them damage immediately, right? So you have no way because it is natural. So we can have 20 minutes break and we will go back.